Okay, so I will briefly give a short lecture and then Guru will continue. We will start with molecular dynamics and I will introduce what it is roughly about and a few technical things. And here first some historical remarks. Perhaps I use my pointer. It was developed in the 50s, I think mostly in the US. This person, Haider, he did a big part of it. And of course, computer facilities at that time were very limited, so they could not study big systems. But they achieved a big thing. This is this publication here. They were able to show that the system, they call it hard spheres, so without long-range interactions, really goes into a phase transition. Yeah? So this was completely unexpected, what they could show here. And there were other publications on this. And here, you see an interesting picture I found interesting. If you look at the publications, this is Bernie Haider and Tom Wainwright, who appear on the publications. And this lady here in the middle, she did all the coding, and as far as I read, and she did not appear on the papers, so this is a bit nasty, I find. Yeah. So, for example, here. And the coding at this time probably was much more complicated as it is nowadays. Yeah. So, what is the basic idea of molecular dynamics? You have a set of atoms, and as I said, they interact somehow. So, what do? We calculate the forces between these atoms. Whatever rule we apply. And you all know Newton's law of motion, that this gives the acceleration of the atoms. So if you have this, it's nearly done. Yeah? So that's all we need, nearly. So how do we proceed? We start with a set of atoms. Yeah, in my case, 5 atoms or so, but normally there are 1,000 or 100,000 or so of atoms. You put them onto some starting positions. Very important, you have to give initial velocities to these atoms. I explain in a moment how we do it. Then if you have the positions and if you have a model for the interaction, you get the forces as derivatives of the interaction energies. Yeah, for example, if we have just two just pairwise interactions, it's something like this. From the forces and the velocities, you can calculate the new positions for a short time step. Yeah? So it is you integrate these equations of motion, you get new positions, new velocities, and this closes the loop here, and then you go on over and over. Besides, probably you're interested in some data to get out, for example, the temperature, the energy, and so on. So that's the basic idea, yeah? Which is rather simple, I would say. Yeah? The tricks are more in the details. I don't know, in German we used to say the devil is hidden in the details. I don't know. So these things are simple. This is also rather simple. I did not mention this, but the kinetic energy, the average kinetic energy corresponds to the temperature via this relation here. So if you want to fix the temperature, beginning temperature, this gives you the velocities. It's just the kinetic energy equals thermal energy. Depends on the number of degrees of freedom, but like this. For the forces, there will be an extra lecture tomorrow, because this is also a quite tricky part. And then this simple step of integration also requires some effort. I will briefly explain how we do these integration routines. This is, if you do so, this is, I think there were already questions in this direction. This is on a particular thermodynamic ensemble. If we do this, of course, the number of particles is fixed. If we don't lose particles via the boundary conditions or so, then we make a mistake. We have typically the volume fixed, so we don't allow for expansion or so. And we have the energy fixed. You can show that if you just integrate the forces, you don't change the energy. Yeah? So this is often not what we want to, as I explained already. Somehow you want to fix the temperature and often also the pressure. So this will be also one of the forthcoming lectures. How do we fix the temperature and how do we fix the pressure? Because one can make some mistakes there. Yeah, just to start, the rest will be handwritten, or I will briefly show the idea. How can we integrate these equations of motion, the Newton law here? The naive approach would be I take the velocity a small time step later by taking the acceleration, which is the force divided by the mass, multiply it with the time step, then you get the new velocity, and from the new velocity you get the position. After this time step you multiply the velocity with the time step, add it to the position here, and you get the new position. This would be a way one could do it, but that's not the best way. I tried to visualize it here. I'm not a big painter. So what happens if you push a cart like this? It becomes unstable and tries to deviate from your direction. Yeah? It's much safer to pull it. Yeah? Then it's stable. Yeah? And the same is true here. So this is called forward integration. Yeah? And the backward integration is more stable. Yeah? So if you take the information from before, so basically the force, here we take the force at the time t, so we better take the force and the velocities from backwards. I think, yeah, this is what we call instability, or in this case you have to do very small time steps. I wanted to make, I say a few words about the integration algorithm. I want to make a short estimate about the time steps before. I hope I made no mistake. I made it this morning. So just to give you an idea about the time steps, what information do we have? I sketched here, I used this simple Lennard-Jones potential I introduced some time before. So the typical depth of this potential is, as I always say, about an electron volt. Yeah? So the typical energies are perhaps an electron volt. Typical distances are several angstroms. Yeah? So that's the range of interaction or the distance between atoms. So if we take this, on, for example, this or such a potential, we can compute the force. The force is a derivative of the energy with respect to location. Yeah, so it's du dx. And if you just say an electron volt per angstrom, electron volt is 10 to minus 19 joule. Without the prefactors, 1.6 I neglect. Yeah? So if you have 10 to minus 19 divided by 10 to minus 10, we have forces of 10 to minus 9 Newton. Sounds very small. But as I said, be careful about small and large if you don't compare with something else. What are the masses of atoms? I think that's roughly the mass of a copper atom or so. It's in the order of 10 to minus 25 kilogram. And then you can calculate the acceleration, force by mass, which is 10 to the 16 meter per square second. This now is a large number. Even these small forces, since the masses are so small. Yeah? Okay. And now we can think how far does an atom travel in a reasonable time step. Yeah? In a reasonable time step, perhaps is a picosecond. I think in the introduction I gave these rough order of magnitude for different processes in solids. So if you take a picosecond, I guess you also know the distance is 1/2 acceleration times t squared. So if you do so, it's 100 angstrom. I hope I made no mistake. So under this acceleration, in a time of a picosecond, the atom would move 100 angstrom, which is, I don't know, 50 atomic distances or so. Yeah? So much too far. This explains that we have to choose time steps which are much smaller. And the typical time step we apply in molecular dynamics is a femtosecond, 1,000th of this, 10 to minus 15, or half a picosecond. Yeah? There's another estimate for this time step. Of course, one could take this time step very short. Yeah? But the shorter you take it, I mean, each iteration in the loop is one time step. Yeah? So if you make it too small, I need too many iterations to reach a reasonable result. Yeah? So if it is too short, I need too much computing time. But if I make it too long, I lose a lot of precision. And that's even more risky. Yeah? Think of this interatomic potential. So if you make a step from here to here, this would mean that you are going deeply into the repulsive region, where normally these potentials are no more very realistic. So this is also not good. And the rule of thumb, how to estimate this reasonable time step, I showed you my little estimate, and it comes to the same results. So 1% of the highest frequency inverse in the material. I don't know how familiar you are with lattice vibrations. In a crystal, you have the highest frequency, the Debye frequency, which is in the order of 10 to 12, 10 to 13 hertz. So if you take the inverse, I took it here for aluminum, you end up with half a femtosecond. So this is one way to estimate the time step required. You can also do it experimentally. You run your MD job for different time steps. I did this here, I think I did it for aluminum, yes, on a small crystal. Here for different time steps, you see it here. I started with 20 femtoseconds time step. You see that the total energy continuously increases. So this means there's something going wrong. As I said, in this system, the energy has to be conserved. And then I made it shorter and shorter. Here's 10 femtosecond, 5, 2, 1. And you see here it's converging. Yeah? So 1 femtosecond probably for this system should be okay. So this is the basic idea, and perhaps I should say a few words about the integration, or you do it as you like.
I will do the link.
Yeah.
And then we can tell them about the other integration.
Okay, then we make it this way. Yeah. Okay. So I mean, there's a handful of different algorithms to do this integration. Yeah. And the most common one is called Verlet algorithm. I did not look up. Do you know where this name comes from? Who is this guy, Verlet? I don't know neither. And there is a variant, the velocity Verlet, and there is something called leapfrog algorithm. There's predictor corrector. There are just called higher order algorithm. So perhaps I can say a few words about these. But for the moment, I think Guru can explain the basic idea of this Verlet algorithm. You might ask, if molecular dynamics is so simple, why did we make all this effort before? Yeah? But this comes tomorrow. Yeah? I mean, if you want to go to other ensembles, you need some more information or some more knowledge. You need the...
So some parts of this is going to be a repetition of what Ferdi just now did. But like we were discussing yesterday, I mean, some amount of repetition is good. So get familiar and you probably start thinking about it a little bit more deeper if you keep hearing it often. So we are going to follow a very simple MD program and it is, like Ferdi said, the NVE is the ensemble that you would think about for this program. And before I proceed, I will give a very short 5-6 slide introduction to MD and then what is the algorithm. So, we are going to spend some time looking at the algorithm itself. How do we initialize, how do we calculate forces, how do we do the integration. Now, there are lots of details which are missing or which are glossed over when I do, because force calculation can be done, for every atom, every alloy, probably there is a potential or there are several potentials which you can use and so on. So, we are not going to go into those details. You will learn about the potentials themselves in a separate lecture. So, for today's purpose, we are going to use Lennard-Jones. So, and then I will follow the Lennard-Jones potential and calculate force, and it could be a little bit more complicated than that. So, Lennard-Jones, for example, has an analytical expression. Suppose if your potential has just numbers, how do we calculate forces, right? So, those are the kind of details which we will not talk about today, but at some point probably we will take a look at. Similarly, integration, I am going to just show you the Verlet algorithm, but there are more detailed lectures that will follow, or at least some discussion that will follow, which will tell you, these are typical questions that people will ask, okay, what is the algorithm that is used and so on. And so, having an idea and having an understanding of why that matters or when you should be worried about which algorithm is being used and so on. So, that will also help you understand these methods a little bit better. So, let us start with MD. This is again a few slide introduction to MD, basically from the point of view of this implementation, this particular C code that I have. So, as you saw in MD, all that we are doing is that we are solving Newton's equations, right. F is mass times acceleration. I have put an I there because now you can think of in 2D Fx, Fy, and that will be according to the acceleration along the x and y direction. You can do it in 3D. Typical LAMPS does it in 3D, but for our purposes this code that I am going to show you, it will do it only in 2D. Okay. And the force itself is the gradient of the potential, negative gradient of the potential. So, you have an independent way of getting the force, and so you know the left hand side. So, you can integrate to get the velocities and positions. And if you know the velocity and position of every particle that you have in your system, then you have completely specified the system, right, for our purposes, because you can get from velocities the momentum that is transferred to the walls, for example, will give you the pressure, and the expectation value of velocity will tell you something about the temperature and so on. So, you can get all the properties of the system by looking at these quantities, for example, right. So, if it is a gas, you can get these pressure, temperature, etc. I am following very closely chapter 4 of Understanding Molecular Simulations by Frankel and Schmidt. It is a very good book. I bought a hard copy some time back. So, please do try to find a copy. I think library also has several copies. It is a good book, at least for beginners. If you are doing MD or MC, it is a good idea to go through this much, at least you should know. It does not go into too much of details. In yesterday's listing, Ferdi had listed several books. There is one by Tuckerman which goes into some detail. So, some advanced things you need, you can look at some of those other books, but at least Frankel-Schmidt level you should know. As you will see, I am going to follow most of chapter 4 today, or at least some 50% of chapter 4 today, and that will give you a clear idea about a simple MD program. So, I recommend that you take a look at this book at some point. Okay. So, this is classical MD, like Ferdi described yesterday. It is also possible to do with first principles molecular dynamics, but that is not what we are looking at. We are assuming that all our atoms or ions are moving according to Newton's law. So, that is what we are assuming, and we are doing this simulation. So, one way to think about molecular dynamics simulations, and sometimes it is very useful, is to think of the simulation itself as if you are setting up an experiment. This clears lots of confusion, and sometimes at the beginning you do not know. For example, should I use NPT ensemble or NVT ensemble, right. So, if you think as if this is an experiment that you are setting up, sometimes it is easier to understand what is happening. So, in both an experiment and in MD, pretty much the steps that you follow are the same, right. You have to prepare a system, right? Okay. You have to prepare a system here also, okay. And then you have to connect it to a measuring instrument, okay. That happens to be solving Newton's equation in our case, and then you have to make a measurement. Like for example, if you want to heat treat a sample, you will put it in a furnace, right. That is equivalent to, we saw thermostating here, because you take a large system and make your system as part of subsystem of that large system. That is what you do, right. Take a furnace, take it to some temperature, and the sample is kept there, so it also reaches the same temperature. Then you will start doing other things like making measurements, or right. So, same thing, you make measurement, after equilibration you are also here also you perform measurement, and one measurement is not sufficient, right. Generally if you are doing experiments, you have to worry about statistics, and here also you have to worry about statistics, okay. So, you can think of both Monte Carlo and molecular dynamics as experiments that you do on a computer. So, that gives you a much better physical feel sometimes when you are having issues, or when you have to make choices, when you have to decide. So, this understanding helps a little bit, okay. And like I said, we always non-dimensionalize when we do these simulations, and in Frankel and Schmidt it is called reduced units. And this is another important thing, like Sushil will tell you, okay, so you are using lamps, and then you are using some metal. In metal, what is the typical length scale, what is the typical time scale, what is the typical delta t, everything it decides, right. So, you should have an idea of these numbers if you are using them to know exactly what is happening in your simulation, okay. Because we are using Lennard-Jones, and in Lennard-Jones we use this sigma as a unit of length to do the non-dimensionalization. That is, every quantity in your simulation which has length will be divided by sigma, and every unit of energy which you have in your system, remember kBT is also an energy, right. So, they will all be divided by epsilon, which is in the Lennard-Jones there, and unit of mass we will divide by m, right. Now, non-dimensionalization, like I keep telling students, is very natural, right. If I ask you what is the cost of this book, what would be the cost of this book? 7,000, 8,000 rupees, right. So, that is what it costs in Amazon today. So, that is 1,000. And what is the cost of this laptop?
1 lakh.
So, why did you shift from 1,000 to lakh as your unit? Right. If I ask what is the cost of this chalk piece, sometimes people will say okay 1 rupee or 50 paisa or something. So, we keep shifting the units. We keep shifting the units because we want to give the numbers between 0 and 100, maybe minus 100 to plus 100 or some such number, right. I can also give this 8,000 in lakhs, right. It is probably some 0.08 lakhs or something like that, or probably you can give that in 1,000, you can say 150,000 rupees. Americans typically do, right. We do not do, we say lakh, but they will say 100,000, 120,000 and so on. So, we typically shift the unit in which we measure things, so that the numbers are in some small range. Non-dimensionalization does exactly that. I mean, I can say that the mass is 10 power minus 25 kg, but I am not going to do. So, I am going to take that as the unit and then I am going to say mass is 1 in that unit. That is what this non-dimensionalization does. While doing non-dimensionalization, the most important thing you have to remember is that okay, how many basic quantities you need. In this case, it so happens that if I have energy, length and the mass, everything else can be derived in these 3. For example, time is sigma times square root of m by epsilon, and temperature for example is epsilon by kb. Because of which you will see that in my code nowhere you will see numbers like quantities like m or kb and so on. No 10 power minus 25s, no 10 power minus 23s, no 10 power minus 10s, right. Maybe integration is femtosecond, but you will not see 10 power minus 12 there and so on. Okay. So, we do this non-dimensionalization so that things are all between some reasonable range of numbers. But this is done automatically in LAMPS by making a choice. You already know that, or you are already supposed to know that you are making choices like that, but sometimes when we want to read values it becomes a problem. So, it is a good idea for you to do this exercise at least some 3-4 times, then you will become very comfortable with doing the non-dimensionalization or dealing with the so called reduced units. Okay. So, I strongly recommend that you do it. For example, why is this unit? It is not difficult. This epsilon is energy, kBT is energy. So, temperature will be epsilon by kb. Okay. So, it is trivial, right. How about this? Why is this time unit is coming as sigma square root of m by epsilon? Okay. So, epsilon is energy, m is mass, and so you can think of half mv squared. So, and v has some length and so on. Okay. So, basically every quantity that you can think of, you should be now able to do in non-dimensional form. So, every one of them will get some combination of these 3 quantities and they will be the scaling factors. When scaled with those, you will get numbers which are lying between some reasonable range of numbers. Okay. Subhash, you had a question?
No, I was saying that it's maybe coming from frequency.
From?
The time and frequency.
Time and frequency, okay, yeah, fine. Okay. This clear? Okay. So, let us look at the MD algorithm now. Frankel and Schmidt has lots of algorithms. This is algorithm number 3, which gives the overall MD algorithm, and these are the steps involved in the overall MD algorithm. Okay. You have to initialize, then you have to start the MD loop. In MD loop, what is involved? Ferdi showed just now the algorithm. You have to calculate the forces, because that is the left hand side. Once you know the forces, you can integrate the right hand side, knowing the left hand side, to get the positions and velocities, that is the integration of equations of motion, and then you have to sample the averages. Okay. So, 4 and 5 for example are determination of forces and 6 integration of equations of motions, and I am not doing the sampling averages, but I would strongly recommend that now that you have this code, go back. There is a way to calculate diffusivity as a follow up of this code that is given as an algorithm in Frankel and Schmidt. You please implement that for yourself and try to measure the diffusivity of one of these atoms, because we saw yesterday, right. I mean, diffusivity is related to the mean distance that a particle would travel. You can tag one of these particles, you can do a tracer experiment in your computer and see where the atom is going, and after a long time how much distance it has traveled, and using the Einstein relation you can try to get the diffusivity, and that is given. Once you equilibrate the system, you can tag one of the atoms and keep following, and from there you can measure the diffusivity in this system, that you can do some transport property you can get using the simulation, but that part is not part of this code. I want you to write so that you will become conversant with these kind of codes, and it is written in C like I did yesterday. You can translate it into Octave, except that Octave will be very slow, or your favorite choice of language. I mean, it can be Python, Fortran, any one of these languages that you prefer. Some say C++, there is some Julia, whatever you want, okay. You use it and try to implement to understand what is happening. Okay. This is again what Ferdi showed, there is the average kinetic energy that should be equal to half kBt. So, for each degree of freedom, so if you are in 3D it will be equal to 3 kBt and the velocity squared, and if you are in 2D it will be 2 kb squared, right. Because of which you can also get the instantaneous temperature by looking at the velocities. Like we discussed yesterday, there is an expectation value for velocity and there is an variance for velocity, and variance is related to the temperature. Okay. So, you can use these relationships. In this, NF is the total number of degrees of freedom, but remember the total momentum is fixed, right. I mean, I am going to take this box and I am going to demand that net velocity or expectation velocity is 0. So, it does not move, because of which the corresponding number of degrees of freedom should be removed. In 2D, 2 degrees of freedom should be removed, but generally, so it will be 2n minus 2 in 2D or 3n minus 3 in 3D, but the number of particles or molecules or atoms that you are considering are so large that let us say in my simulations I am going to have 36 of them. 2 into 36 is 72. So, 72 minus 2 is 70. I should strictly speaking use 70, but I will use 72, saying that approximately they are the same. This is much better in actual simulations where you typically have 30,000 or 50,000 atoms, and in 3D. So, that will be 150,000, and you are subtracting 3 from it or not does not matter much. Okay. So, Frankel and Schmidt has this also as a note. Sometimes if you are looking at the first time at the code, it is not clear where did the 3 go, why is it not removed. So, these approximations are also pointed out in the book. Below the algorithm it is written note that we make the approximation that number of degrees of freedom is 3n itself, not 3n minus 3 and so on. So, that is what I am also going to do. In fact, even the notation that I have used in the code is exactly what is given in the algorithms that is given in Frankel and Schmidt. So, if you have the book, you should be able to follow line by line. I have also taken their comments and incorporated them in the code. So, you will clearly see which part of the code corresponds to which part of the algorithm. Okay. Okay. So, this is algorithm 4 from Frankel and Schmidt. Yep. Because you have these velocities, you are going to take the average velocities and you are going to make the average velocity to 0.
The sum of all velocities is 0.
Yeah, the net velocity there should be 0 for 3 degrees of freedom. Yeah, so the 3 should be removed. So, we need to initialize, this is algorithm 4 from Frankel and Schmidt. So, you take a lattice, I am going to take a square lattice and I am going to populate the lattice by putting atoms at these points, and I am going to give random velocities to them, okay, and calculate the velocity center of mass and calculate kinetic energy. Kinetic energy is related to temperature, remember, okay, and then scale the velocities so that it will correspond to the temperature that I want. I will set up a temperature for my simulation, so it should correspond to that, and set the desired kinetic energy and set the velocity center of mass to 0. So, I have the now temperature is set for my system, and the box will not move, there is no net movement that will come because of this. Otherwise, if I give random velocities, you add them all up, there will be a net velocity for the box, okay. And this is a genuine problem. I mean, I think we have also spent some time, you are not paying attention to this, and what do they call some flying moon or flying ice problem or something, yeah, that is something it is called, okay. So, those of you who do FEM also know, right? Anybody does FEM simulations here? Why do we fix a point? Why do we put roller support? Right? Because it cannot have rigid body motion, it cannot have rotation, right? We put this. So, similar thing here, you need to make sure that it does not just take off and moving. So, and you also calculate the position in previous time step in this initialization. Why are we calculating the previous time step? And it is an approximate calculation, it is not very exact, will be clear when I show you the integration. The Verlet algorithm, if I show you, then you will understand why you need to initialize the previous time step. I am starting the simulation, and I need a previous time step to kickstart or bootstrap my calculation. So, I calculate that also as part of the initialization. I will show you the code, you will see exactly how it is done. Okay, so this scale factor is clear, V alpha squared is kBt by 2m, and you can see the scale factor is 2t by v squared because we are in 2D. If you are in 3D, it will be 3t by v squared, where t is the instantaneous temperature. Okay. So again Ferdi has showed, and probably you will keep seeing this again and again. So it comes from equipartition of energy, and it is important. So these are the places where you make contact with your StatMech, whatever you have learnt in your statistical mechanics, how is it exactly being implemented in the code. Like I said, the integration of Newton's equation of motion, we are going to use an algorithm which involves the current and past time steps. So that is why we calculate the position at previous time step. Again, this is also explained in Frankel and Schmidt. So algorithm 5 is the calculation of forces and energy. Okay. So you initialize the forces to 0 and then you loop over all pairs. Okay. So what is it that I am doing? Let us say that I have a box, let us say that I have particles. Okay. Let us say that I am able to label them. Okay. Now, when you calculate forces, right, the forces on 1 will be because of 2, 3 and 4. Similarly, for 2 will be because of, right. So, all of them, why? Because we are only considering pair wise interactions, right, it is Lj. For a pair of atom, there is a force that you can calculate. What is the force acting on this because of this, because of this, because of this, and so you can calculate the net force acting on this and so on. So, you can calculate, and Lennard-Jones also tells you that this force only depends on the separation, right. It does not depend on, you saw that Lennard-Jones is written as R, where R is square root of x squared plus y squared in 2D, x squared plus y squared plus z squared square root in 3D. So, it is only dependent on the separation, not really on the direction. Okay. That is why you will see, even though I start with a lattice which is square, the potential cannot support the square lattice. All directions are equivalent. It will not distinguish 1 0 from 1 1 in the 2 dimensions. So, it will take this lattice and make it into a triangular or hexagonal lattice. You will see when I run the simulation, it will undergo this transformation. Okay. So, you need to loop over all pairs and you have to implement periodic boundary conditions, and because of periodic boundary conditions you can see that no particle will be at a distance greater than half the box length. Why? Because any particle which is at a distance larger than half a box length, because of periodic boundary conditions, will be at a distance which is smaller than half a box. This is the one that I was telling you about, you know. When you have periodic boundary condition, you can't put 2 particles at this distance and expect that they are too far off, because they are just next to each other because of the images from the other side, right. So, because of which our periodic boundary condition implementation, you will see that we will take box by 2 and subtract a box to get it back. Okay. And we also do one more thing. Okay. So, that is also important. Let us say that this particle is having a Lj interaction with this, and this is at a distance, this is at some distance, this is at some distance, but this distance is much more than all these distances, right. So, if you do Lj, you saw the potential, Lj potential goes like this, right. So, probably at this distance it is much closer to 0. So, as you will see, force calculation is one of the costliest parts of the MD algorithm. Okay. So, there is no point in calculating force for a particle which is so far away that the force contribution is going to be so small. So, we generally define a cutoff. We say that any particle which is at a distance larger than the cutoff, we do not calculate, and this causes another problem, right. So, let us say this is where my cutoff is. then there is a discontinuity here, because there is a force acting on the particle up to this point, suddenly beyond this point it drops to 0. That can cause problems. So, sometimes you have to correct for it. The way to correct for it is to shift this in such a way that it reaches 0 at that cutoff point. Okay. So, these are, I mean, details, like Ferdi was saying, the devil is in the details. Okay. So, you can do these things, but you have to pay attention to what you are doing and make sure that that does not cause you any trouble. This can lead to lots of numerical difficulties, especially if the particles are moving a lot, because it will see suddenly force will vanish on a particle. That can cause numerical instabilities. So, we check cutoff, and if the particles are within the cutoff, we calculate the potential or the force or both, depending on what you want to calculate. If you want to calculate energy, then you need potential energy, then kinetic energy using the velocity, and if you want to, for integration anyway, you need the force. So, we update the forces and we update the energy. Energy is basically a sanity check in this code. So, we keep checking that energy remains constant. So, this is the algorithm for this, and we use the reduced form. Like I said, there is no sigma, no epsilon, no m, nothing. So, you can see that is the potential for 1 by 6 to the power 12 minus 1 by 6 to the power 6. This is the repulsive part of the potential. Okay. As you come closer, this will take off very steeply, and this is the attractive part. That is why the signs are different, and the repulsion is much steeper than the other side. Okay. So, that is why sometimes, for example, for getting the lattice parameter values, you have to do simulations. The way we do simulation is that we take a lattice parameter initially, which is larger than the equilibrium lattice parameter, and see if the system relaxes to that value. You can also take smaller than the equilibrium value and see if it relaxes to this. Sometimes smaller than can cause you problems, because smaller than this lattice parameter, if you are not careful, might take you somewhere here, where the forces have become positive, which means it is like a bomb, the two atoms will just fly off. Okay. So, you start with a lattice, and the lattice might go to pieces or cause you lots of grief, maybe some sec faults or maybe some nonsensical answers and so on, which is true in real systems also, right. This is the explanation as to why when you heat something there is always thermal expansion, right. If the potential was perfect on either side, on the average it will be the same size. That is not true, because the atoms, when they are vibrating closer together, is much harder than farther apart, because the potential looks like that. That is why with temperature, when the vibrations increase, they tend to pull apart a little bit, which is what you measure as the thermal expansion. So, it is the nature of the potential, which is what the LJ is capturing. I mean, LJ is very simple minded toy potential, but it is still capturing some of these aspects. And so, when you are doing simulation, you have to be also careful. We say that, for getting the lattice parameter, you have to do several simulations away from lattice parameter and see that you relax to the same lattice parameter. That is how we know that the calculation is correct. While doing that, even though on the one side you do not really have too much of constraints, you can take whatever lattice parameter. Let us say it is 3.04, you can go to 3.06, 3.08, 3.1, 3.2, maybe it will take longer, but it will converge. But on the other side, you can't go to 2.6 and expect that it will converge. You can go to 4.2 and expect it to converge, it will converge, right. So, it is important to know these things. Okay. And force is just like I said, you take the potential and you take the gradient, the negative of the gradient is the force. Okay. So, there is some algebra there, which also involves, which some of you might have done, at least the physicists here would have done. So, because r is x squared plus y squared square root, when you take with respect to x, etc., there is a half that comes, and then the thing goes to minus half in the denominator. So, there is an r that shows up in the denominator and so on. So, it is just algebra. Okay. It is there. Is this clear? Okay. So, this is not calculation of forces, this is wrong. I will correct it before I post it on Drive. So, this is the algorithm for integration. We start the MD loop, we use the Verlet algorithm, and we calculate the velocity. Well, algorithm will give you the positions and you calculate the velocity, then you calculate the velocity center of mass and you calculate the total kinetic energy. These two you have to do to make sure that you are scaling for the right temperature and that your net box is not moving, and you update positions for the previous and current time, okay, and calculate instantaneous temperature, total energy and so on. You can measure any number of them. I mean, these are the only two I am showing in the code, but you can measure other quantities also, like mean square displacement for example, which will give you diffusivity and so on. You can. Okay. So, the sanity checks that you do is that energy remains approximately a constant and velocity of center of mass, velocity center of mass remains at 0, they should not change. Now, what is this Verlet algorithm? You take the position of a particle around the time t and you Taylor expand. R of t plus delta t is RT, right, and plus dou r by dou t del t. Dou r by dou t is nothing but velocity Vt, and 1 by 2 factorial del squared r by del t squared, which is acceleration, which is nothing but force by mass. 2 factorial is 2, that is why f of t by 2m del t squared, and there is one more term. What is the third derivative with respect to time called? You have velocity, you have acceleration, what is it called? In mechanics there is a word, so jerk, right. So, I have the jerk term also. I am having that term because as you will see, I mean, we are getting a little bit more than what we bargained for, and then there are terms of the order of del t to the power 4, right, that is the Taylor expansion, and I can take small enough del t that del t to the power 4 will be negligible, okay. And you can also do for t minus del t, there is a Taylor expansion you can do, right. All the odd terms will get minus, other than that it is the same. You can add them both, because velocity is an odd term that will go away. So, just from position, knowing the force and hence the mass and hence the acceleration, you can replace there. So, you can see in one step r t plus del t plus r t minus del t is 2 r t, f of t is known, m is known, del t squared is known. What is the only thing that you do not know? T plus del t. If you know the current position and if you know the previous position, you can get the current position. That is all you need, you do not need to have the velocities. Then knowing the previous position and the future position, you can estimate velocity. But remember, this velocity estimation that you have has an error of the order of del t squared, okay. It is not very approximate, I mean very precise as compared to the position determination, okay. But why do we need velocity? Only for making sure that there is no net change and temperature scaling, right. So, because of which this much accuracy is sufficient for our purposes, we do not bother too much, but positions are evaluated at a much higher accuracy level, 2 orders of magnitude higher level than the order of accuracy for the velocity. Is this clear? Okay. So, this is the velocity Verlet algorithm, which is what we have implemented. So, I get knowing the current position and knowing the previous time position, I can get the future position, provided I know the forces which come from the potential, and mass anyway we are going to normalize, and del t squared is the time step that we are taking. Okay, that is all that is there to this algorithm. Like I said, you know, one afternoon we wrote several MC codes, right, some Glauber, Kawasaki, everything you can write, and one afternoon you can also write a very simple minded MD code. They are not very difficult as concepts to understand. The rest of it is all details. If you know this much and if you are very conversant with these things, then the details you can go pick up on your own. You do not need anybody else to teach, even though we are going to spend another 8 days teaching you more stuff, but you really do not need. I mean, this much if you know, you will be able to do rest of the stuff on your own. Okay. Okay. So, let me now go back to the code. I hope the code has been uploaded. I started with the summary of the algorithm. The algorithm has only few steps. This is the summary of the MD. We initialize, we start the MD loop, and the loop requires force, which is on the left hand side, and integration, and then whatever you want to measure. Right? F equal to ma is what we are trying to solve. So, F I have to calculate. Once I know the potential, I can calculate F. Then I can integrate. Then I can keep doing this for every time step. That is the MD loop. And before doing that, I have to initialize. That is all that is there to the algorithm. It's clear? Okay. So, the code is in place. So, you can download if you want to take your computers, and if you want to walk with me, you can. But in any case, I will also go through the code. Okay. This is a C code, and there is a readme file which tells how to deal with it, and readme file basically tells that if you say make, okay, you will get an executable. I can remove a dot out first. So, there is no a dot out. If I say make, I will get an a dot out, then dot slash a dot out, it will run. Then you can go to the output directory, and my favorite plotting tool GNU plot, and then load the plot.plt, and it starts with a square lattice. Can you see it is already going to, you can see that it makes these, or right, more or less. There are movements, because in any atom there will always be some jostling, some vibration, some movement, but you can see that even though I started with a square lattice, it has transformed and it has gotten to a triangular lattice. This is because this is at a very low temperature. Okay. I can also take it to a very high temperature, so that it will lose the lattice structure completely, it will become a liquid. You can do by changing the temperature. Okay. And it is doing this because LJ is isotropic, right, it does not care about any direction. So, you can't get something like cubic out of the LJ. Do you also notice the periodic boundary condition? Right, some of the particles there, they keep jumping here and there, that is because if it leaves here, it has to come through this side, right. So, you can see that my periodic boundary condition implementation is okay, and I think I run to some 10,000 steps, and we are also going to learn about the lattice vibrations or phonons, right. So, if you assume that it is a perfect triangular lattice, with respect to which how the atoms are moving, will tell you what type of waves you are setting up in the lattice, right. That is basically what waves are. I mean, you take a mean position about which different points, different movement is there, which you will measure. Okay. So, this is how you run this code: make, execute, go to output, open GNU plot, load the plot.plt, you will get this movie to watch, and you can change the parameters in the code. It is not really very professionally written code, in the sense that every time you change a parameter, you have to make once and so on, but I wanted to keep the code as close to what Frankel and Schmidt gives as possible. Okay, so, this code is originally from 2011. I made some modifications by adding comments, etc. So, that is why it says 2022, but primarily, I mean, I did not change any part of the code at all, it is just the comments. So, this is all standard, include the input output library and the standard libraries and math, etc. Then there are file pointers for writing output files and so on, and there are variables that you have to have. The number of particles is here, okay. N part is 7, so 7 minus 1 is 6, so 6 by 6, 36 particles. Did you see 36 particles? Was there 36 particles in the simulation? Do you remember? Can you see 1, 2, 3, 4, 5? Okay, maybe it is probably easier for me to show you in the other one. Okay. You can see 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, okay, 6 by 6. That is what the number of particles or atoms are. We are saying particles because they can also be molecules. It is called molecular dynamics because you can also take molecules and make them do the same stuff. Okay. And here is the temperature. Temperature is 0.01. Remember, it is all reduced or normalized. Okay. I can, and this is not inverse temperature. Yesterday I was using inverse temperature. So, there if you took 10, it corresponded to 0.1. Took 100, it corresponded to 0.01. That is not the case here. So, you can try to run for a higher temperature also. You can give 2 or 3 and see what happens, and that is something that you can do with the code. And yep.
So in the code you are writing n part is equal to 7.
Yep.
Then number of particles is n part minus 1 into n part minus 1.
Yeah.
So the total number of particles in the system is 36.
Yeah, only 36 because n part is 7. So, n part minus 1 is 6, 6 into 6 is 36. Now, why am I giving that n part 7? Yeah. So, you want to put 6 particles on a lattice. How many distances you need?
Okay, sir. So you are doing a grid spacing thing.
It's just a trick. You, I mean, you don't have to. You can also give n part 6 and you can add 1 and whichever way. I mean, it's not. These are non-standard. You can do according to your wish. Yeah. Okay. So this is the box size, and I find out the distance between the particles, that is A, which is box by n part minus 2, and then box I scale. I make sure that no, I got the box size exactly. You can try to do it. Yeah.
So the box size dimension is also scaled.
Everything is scaled. All lengths are scaled by sigma. Okay. And this is the cutoff radius, and this is half the box radius. Okay. So, you can see 5 divided by 4 and plus that. Okay. So, what does this do?
So here you are spacing each particle
On a lattice. So, it is basically for to make sure that I place them correctly. Okay. Now, there is a error message here, cutoff radius greater than half box length and quitting. Why should it quit if the cutoff distance is greater than half box length? Right? What will you get? You will get infinite regression, right? So, we said that we are using periodic boundary condition. So, no particle can be at a distance which is larger than box size by 2. So, which means the cutoff for the potential cannot be greater than box size by 2. If so, then I will be calculating from this side, I am also calculating from its image and from the image of the image and so on. So, it will give me errors. So, that is why there is this error message. If you can try, you can give the box size something and give the cutoff radius to be same as box size, it will quit, because that is wrong, you cannot give. Okay. This is not part of the algorithm. Okay. So, it is not there, Frankel and Schmidt does not have it, but after you make several times this mistake and getting wrong answers, you realize that it is better to put this. I should not randomly change some number and then look at why my code is not working. Okay. Okay, and this is the cutoff I said. For cutoff, what do you need? Your potential is 4 times 1 by r to the power 12 minus 1 by r to the power 6. So, I calculate r to the power 6, and if I pull out one r power 6, it is 4 into 1 by r power 6 into 1 by r power 6 minus 1. So, that is what is being calculated. So, that is the cut that we are calculating. This is the delta t, this is the time step for integration. Okay. As you can see, this is of the order of 10 power minus 3, which means my positions are accurate up to what? To the power, no, position 12 in the, it is not angstrom, in the reduced units, in the units of sigma. Okay. So,
Sir, but ultimately my time step, like say in the reduced unit also, it turns out to be like, say like the way I non-dimensionalize it,
yeah.
say like it turns out to be in femtoseconds somewhere.
Yeah, it will always turn out to be in the right measure for that potential. Okay. It is femtoseconds we calculated for some metals, for aluminum using that, some other system it could be something else, but it will, non-dimensionalization has that advantage. Okay. It will make sure that things are all in, as long as you have done the non-dimensionalization properly, it will automatically take that into account. Okay. Okay. So, initialize MD, what am I doing? Putting the lattice, and here I am not using GSL or anything, okay, because I am really not into calculating statistics. If so, I should use one of those proper random numbers. Okay. Here I am just using rand max and then giving a random velocity to the particles. Okay. So, that is initialization. You put the particles on a lattice and you give them a random velocity, which is what helped the particles go to their equilibrium position, right. They were sitting on a lattice, but they were randomly moved, which allowed them to jostle down to the right kind of structure by themselves. Okay. These expressions are there in Frenkel and Schmidt. Okay. So, when he says change the velocity or give arbitrary velocity, etc., the whatever is the expression that is there, that is what I am implementing here. Okay. And you calculate the velocities, you calculate the square of the velocities. This is basically for calculating the kinetic energy, this is basically to make sure that you are not having net movement. Okay. So, you do this, and n is the number of degrees of freedom. Remember, I said that I am not subtracting this 2, I am going to keep it whatever n is as is, right. Okay. And this is the scaling factor. I showed you 2 times temperature divided by V squared, square root, that was a scaling factor, that is a scaling factor, and now all the velocities etc. have to be scaled, and this is where I am calculating the previous time step position. Okay. And it is a very approximate calculation, right. I took x minus v times t, delta t I took. So, but that much is sufficient for me to bootstrap the algorithm, because my first step I am going to need what is the previous step to calculate what is t plus del t, right. So, current r of t I have given, and using that I also calculated an approximate previous time step. Remember, did I use anywhere the velocity distribution to be Maxwell-Boltzmann? I have not. Okay. After you do the simulation, it should turn out to be Maxwell-Boltzmann. You can check, you run this simulation for a while and then start dumping the velocities and dump for some time, and then look at the histogram of the velocities, you should see a Maxwell-Boltzmann. Okay. But we are not putting it, it will automatically come out of the simulation. Okay. So, initialization is done, then I am going to write the initial profile, and I am creating all this plot.plt, so that later it is easy for you to visualize, and here is where the MD loop starts. And what did the loop involve? Calculate force, integrate. You want to calculate some averages etc., you calculate some sanity checks, energy etc., you will calculate, right. So, this is where the loop starts, and first thing is to calculate the forces. What are the forces? Force calculation, basically you need to look at the distance and you have to make sure that that is consistent with periodic boundary condition. That is all that is happening here, right. You calculate I and jth particle, what is the x difference, what is the y difference, you calculate the r, which is x squared plus y squared square root, and make sure that the components themselves are not larger than box by 2. If so, you subtract a box, so that if a particle is there, you subtract a box, so that it will be on this side, that will be your distance between the particles. And this is the cutoff. Why do I have R2 is greater than 1 e power minus 12?
Sir, so that is the distance where like it is becoming extremely my potential is reaching up to infinity. So
Correct.
the forces are like the tangent is extremely steep.
Right.
The forces will be very large.
Right.
So I have to keep a cutoff distance which is at least greater than that distance. So if I just look at the LJ graph, from that I will get that distance. So for that only I am keeping.
Strictly speaking, you should not be in that regime. I mean, no particle should come at a distance less than this. Okay. So in principle, you don't need. I mean, if you start on a lattice where they are so far apart, etc., should not happen. But if by mistake anything happens, two particles came together and they are flying and then they are reaching close, etc., in those cases also it will not give you infinity. Okay, it will not blow up. So that is why it is there. That is why in the algorithm you see this is not there. You only check whether it is less than cutoff. You assume that they will not come this close. Okay. But if you did any mistake in your velocities, if you did any mistake in your initial configuration, if you did any mistake in your time stepping, by mistake if the two atoms come too close to each other, in those cases this force will not be calculated. Okay, it will not, so it will not give up. Strictly speaking, what should have been done is that if it becomes like this, the program should quit telling you which two atoms came too close to each other. Okay, that will be the proper code. Okay. Anyway, so this is 1 by r squared and r power 6 is 1 by r squared multiplied thrice, and then the force is this, and the force components x, y, etc. And then when you calculate energy, remove the cutoff energy, because at that point is where you are stopping. Beyond that, whatever is there is not part of your energy. Okay. This is the integration. Integration should again be consistent with, so this is what you saw, right, 2 times x minus previous plus del t squared times f t by m, m is not there, it is all normalization is gone. So that is it, done, we have integrated, we now know the future position. So I have to make the current position as the position that I took for calculating the future position as the previous position, and the future position becomes my current position. So I can move to the t plus del t, right. I start with r minus t minus del t and t. Now I calculated t plus del t. So t goes to where t minus del t was, t plus del t goes to where t is. So I will calculate t plus 2 del t. So that is all I need to. So this is consistency with periodic boundary condition, and then I say okay, these are the, this is the velocity evaluation. Again you have to calculate the velocities and energies, etc., and then you make the current time as the previous time, and then it goes back to the loop, right. Write the output.
Sir,
Yes.
can you just scroll up? Sir, a bit more up. Says here when you are finding xx and yy, so like these coordinates can go outside the box also?
They will not, no. They are done only if,
Sir, no, like I am saying just the 2 lines below the for loop, just the 2 lines below the for loop, where sir you have where you have implemented the Verlet algorithm.
yeah, I have implemented Verlet here, right.
Exactly.
Yeah, okay.
Sir, in these 2 points, whatever xx and yy I get, they might go outside the box.
Then I will bring them on the other side, no, that is periodic, that is what I am doing.
Yeah, so sir, you
If it goes outside of the box, I am bringing it from the other side, and if it goes outside on this side, I am putting on that side. That is periodic.
After that, you are doing this XR and YR.
Huh.
Yeah. So, sir, this is like the difference between this new position and the old position.
Okay, let us say one atom went out, I brought it on this side, but the atom, its previous position would have been on that side. So, when I calculate the distance, again I have to be using periodic boundary condition, calculate the distance, right. See, it went here, it came this side, but the distance it travelled still consistent with periodic boundary condition only that much. So, I have to do that. Otherwise, you will think that this atom went from here to here, this much is the distance. In other words, consistent with periodic boundary condition, whichever is the shortest distance is what we will consider, not the longer distance. So, that is what being done. So, this periodic boundary, like I said, I mean this is not very efficient code again, I am doing very brute force because you have to understand what is happening without having to worry about the tricks. That is it, I mean it is 269 lines and most of it is repeating some lines. So, the integration was done in 2 lines and the force calculation, energy calculation was done in probably another 6 to 8 lines. So, total 10 lines you have a basic MD code working, okay, which is there in one of the elementary textbooks, which is one of the first MD codes you are expected to write. They should all be consistent with period. Yeah. Like I take one particle, it goes all the way and then it comes there, then it is not that full box length. It is as if it went there, that much is the distance, okay. But probably if you are doing MSD, you should make sure that there is not too much, I mean, okay, it will go and then it will again come back, it can even come back to 0.
Sir, no, but I am saying that, like, suppose if I am doing MSD.
Right.
So the way the MSD is formulated is that from a reference time, I then measure the position at different times. And
Right.
then I
Calculate the net displacement, yeah.
So like then I calculate a mean square displacement and then I do a gradient with respect to time and divide it by 6 or 2 based on my dimension. So, sir, when I do that calculation of the difference in the distance when I am calculating, so like that difference also needs to be applied with the periodic boundary condition.
Yes. And you should do large number of simulations so that some cases where it went, some cases where it went from there below, everything will be accounted for. Statistics should be.
I think if you just sum up the small steps you do, then you don't need to apply the periodic boundary conditions. I mean,
No, but like that was my question, that after each step, do I need to check for PVC?
I mean, if you just measure as you said, the distance to the initial position, then of course I get a problem with the periodic boundary conditions.
Yeah, correct.
But if you
What he is suggesting is every time when you are moving, you already keep track of how far away you moved.
then you avoid this problem. I will show later on in one of the, I think next week, diffusion problems in Monte Carlo, and there I did the same, and that works nicely.
Okay.
Just one little remark,
Yeah.
just play with your code a bit.
Yeah.
When I doubled the system size, box size, you can show, I mean, it's
Blowing up? Huh?
blowing up the box without blowing up anything else. Worry about that. I mean, these cutoffs. I think some time ago it was one of the goals to predict stable phases using MD. And then people were very proud that they were able to put something, to really have a transition from FCC to BCC, so like in iron, for example. The trick was just to put the cutoff to the right position. So once the atoms are far apart, then they feel other parts of the potential as if they are closer. So that's a kind of fake transformation. I mean, you can do that, but it's not very reasonable.
Okay.
And sir,
Yeah.
applying PVC condition, so what you have done, we are checking where the particle has moved from the box on the right hand side and left hand. Rather than can
Yeah. So, there are other kind of implementations that are possible, but I have taken a very brute force this thing just to show you that okay, if it goes out you bring it back on the other side. I mean these are not very efficient code, okay. So, the other implementations are possible, and probably if you look at some, you can look at source code of lamps and things like that, right. So, you can take a look at, and some of them probably do these, like Ferdi himself said yesterday, right. The periodic boundary condition, the way I had done is by wrapping, but you can go like this and then connect the last one to the first one, that is all.
Franklin fruit we are taking low image condition in the chapter 4.
Okay, but that is not what they give in the.
This minimum image convention is more if you want to calculate the distance, say, between two precipitates or so. So you have one precipitate here, you have one here, but your box ends here. So which distance do you use? Do you use this distance, or do you use the distance to the periodic
Because of the
image?
image.
Yeah? And this is shorter, perhaps, yeah? Then you use the smallest one. So this is one of the rules. I don't know whether it's even justified or to do it that way.
Yeah, I mean the system will see that, suppose if it is elastic interaction for example, that would be the relevant one, right.
Okay.
Or if you are pushing a dislocation through, that will be the relevant distance. To that extent, yes, that makes sense, but it is not.
Sir, this is what we were saying.
Huh.
Sir, see, here they are saying,
When we are calculating
so when we are calculating this, so like this is they are looping over all the pairs. So I start from I to n part minus 1 and then j from I plus 1 to n part. Then I am calculating XR is equal to, so this is for.
So he also makes a comment about n int and how Fortran implementation, etc. Yeah, you can do that. Like I said, I am showing because I want to make it explicit. This is what happens. If it goes out, I am bringing in. Yeah, that there is a comment about n int also. I don't know if you have seen. He has a footnote saying that he is not happy with the Fortran n int. He says, you implement your own n int, because some of the Fortran compilers, this implementation is terrible, and because you have to use it so many times, this is slowing down things, right.
A long time back when I wrote a MD code, I wrote it in C++. So that time I had used the round or something like that.
So that's what I mean. He has a footnote where he says, unfortunately, many Fortran compilers have a bad implementation.
I mean, typically,
So when I wrote it with a round,
Fortran users like me, we always used to write int without the n plus 1/2. This is n int, and then you are on the safe side. And this is typically.
Okay. Yes.
we are implementing temperature
Ha.
in simulation.
Ha.
So that is how it is correlated to the real temperature. This point not 1. So it is 1/2 kVT into 1/2 mv square. That.
No. So there are two things. One is that in a system, the temperature is related to the variance in the velocity of the particles that make up the system. That is the statistical meaning of the temperature, right? What is it related to? What we call as temperature basically is a measure of how the velocities are distributed. Higher the temperature, more will be the distribution, or the variance will be higher. That is the part we are using for rescaling, so that in the simulation I can set the temperature. In fact, you are going to learn the scaling is really bad way of keeping temperature. That is why thermostats, etc. There will be a lecture. You will learn. You have to go back to the StatMech concept that was taught this morning. That what is a thermostat? It's like another bigger system. How do I maintain copper temperature? Suppose if I want to keep it at 800, what do I do? Take a furnace. The furnace goes to 800 and put this thing, right? So that is my thermostat. Similarly, I have to take a larger system which is not affected by the changes that will happen to it. It will still maintain its temperature, right? For matter you call an infinite reservoir or something like that, right? So similarly, there should be a reservoir which gives heat, takes heat, but its temperature does not change, so that whichever system is in thermal contact with it will also be in the same temperature. That is the temperature that we want to maintain. So, this scaling is not a great way of doing it, but there are other. So, you will learn how to do that. So, that is what the temperature corresponds to. What we are doing with scaling, right? So, temperature will be 300 Kelvin, let us say. That is, if you take a molecule which has a mass of 10 power minus 25 or something, and which has a lattice parameter, let us say 3 angstroms and so on. I do not want to put 3 angstroms, 10 power minus 25 kilogram, and Kb is 10 power minus 23 and so on. So, I scale, I make 10 power minus 25 as 1 unit, right. If I do that, then the temperature even 300 will be reduced in some number, like we did, something is in lakhs and something is in 10,000, something in paisa, like that. So, we have a unit where the range will be restricted. That is why I am using 0.01. So, there are 2 steps now. You can use from the reduced scale, measure what the actual temperature corresponds to, and remember that temperature itself for different systems, right. I do not know if you have done this exercise any time. We kept telling that at the melting temperature the number of vacancies is 1 in 10,000, right. But lead might melt at some temperature and tungsten might melt at some other temperature. But at melting temperature for lead and for tungsten it is 1 in 10,000, right. So, what are we doing? We are scaling by the melting temperature, we are normalizing for the fact that something melts above 2000, something melts around 200, but okay, I mean that does not matter. If you account for that, then they are the same, right. That is what the scaling is about. So, that temperature 0.01 corresponds to what will depend on what is the bond energy. Basically, how much is the bond energy breaking is going to cost. So, how much is the thermal energy, how much will it be able to break and so on. So, that is the non-dimensionalization or reduced units part. So, there are 2 aspects, one is the statistical aspect which talks about how to connect the velocities of these particles to temperature. The other one is a real system, each system will have its own parameters and a corresponding temperature at which things will happen, and how are we scaling for it. These are 2. You can by going from reduced units to real units, right. I took a sigma and that sigma is a measure of interplanar distance. Now, that interplanar distance could be 3.4 angstroms for some system and 4.04 for some other system. So, like that you have to go back, okay, I changed all length scales to this, I changed all the energy scales to this epsilon, and that bond energy could be different for different systems. So, what is it for my system? So, like that you can calculate and go back to the actual temperature for the system you have in mind within this model, assuming that it is described by LJ. Okay. You will get a temperature and that will be the realistic temperature or near about the temperature where you would expect things to happen in that system. That is one. Irrespective of what that system is, what that number is, corresponding to that temperature the atoms will have a specific velocity. So, the temperature velocity relation should also be satisfied. That is the statistical mechanical aspect, that is on the average if you calculate that should correspond to some temperature, that is the other one, that is the statistical mechanical one. And we have taken into account both, the Fs, the scaling takes into account this, and the reduced units takes into account that 300 for, I mean I can call this copper and maybe it is 600 for copper, I can call it some tungsten, maybe it is 1800 for tungsten, everything is then done using one simulation. Understand? Any other question or clarification? Yes. How do you know system came to equilibrium? So, you have to dump potential energy, kinetic energy, mean displacements, right. Initially it started from square, if you look at the average distance between particles it would be some value, but after it came into the triangular lattice it would have some mean distance. So, all of them will go to a constant value, but they will fluctuate about that constant value. Depending on the system's temperature the fluctuation will be higher and higher, because remember it is entropy, higher temperature, it will explore even those which are slightly costly and so on. So, all the things Ferdi had a figure, right, with different femtoseconds he was doing initially it is, and then they will stabilize at some value. So, for the given parameters then you have equilibrated for that system, but the fluctuations you will see. But this is a very simple minded code, and there are other issues that Sushil knows about. If you use barostats and thermostats etc., there is also, you know, for example, you might think that you have kept the pressure at 0 atmosphere or 0.001, but it will be fluctuating. Okay. So, there is something unphysical that is happening there, that is related to the simulation, and Ferdi will also probably talk about some of those aspects. But in general what you do is that you measure some of these quantities and they will go to a constant value, but they will fluctuate about the constant value, and the fluctuations will depend on what temperature you are in, and then we know that the system has equilibrated. Then you can start making measurements. For example, lattice parameter, start from a higher value, then you allow it using EAM, for example, for aluminum. You start with some 4.15, it will go to 4.04, and then it will be having very small fluctuation about 4. Then we know that okay, it has equilibrated.
So, is that fluctuations like the vibrations are numerical?
They are statistical, they are statistic, right.
So, you have to use some damping factors on which to control.
So, those damping factors are the unphysical ones. So, that is why you might get something which is not okay if you are not careful. But lattice parameter you take from 4.15, slowly it will go, and about 4.504 it will do, and probably for lattice parameter the fluctuations are very, very minimal.
But only if you are at constant pressure.
At constant pressure, yeah. So
if you are at constant volume, like here, the
yes.
atoms pull on the boards,
Yeah.
but they cannot get closer.
Yeah. Yeah, which ensemble here?
It's an idea to calculate the pressure.
Here
In this example, there should be a negative pressure, yeah, if you would calculate it.
How do you calculate pressure?
Sir, we calculate pressure by, so we do a virial calculation and we do the kinetic energy as well. And from that we calculate using the volume.
Okay. So, I do not know if you are getting to virial any time. Stresses.
After tomorrow,
Come back.
Sir, with that calculation actually, when we use Bromax, we use it like a black box and we get the.
Yeah. So, that is the point in this course. So, we want to talk about some of these things, what is behind and how is it done and so on. But given the short amount of time, we will still try to do as much as we can. Yeah, okay.
I'm not sure whether I explain the virial, but I at least use it, as you said, for the pressure. Yeah, I have to look up what I in my notes here.
Okay. Any other question?
So, just going to that. So, you had a cutoff for the potential. How, where was it? Okay. That you make sure that the value was taken care of.
Yeah. So, everything was scaled by sigma, right?
Yes.
And the sigma actually corresponds to, in Leonard Jones, this distance, so where the minima is. So, basically it is a lattice parameter. So, when I say 2.5, what I am assuming is that beyond the second nearest neighbor, the interactions are not important. You can actually calculate what that value is, because E cut is there, you can print it out and you can see what that value is. Again, like Ferdi said, some number is small or large, it depends on with respect to what, right, with respect to the bond energies and interaction that you would get at these points. Then if it is very small, then you can say that okay, this is a good cutoff, it will not affect our simulation results. Of course, if you take 1.1 or something and cut off, right, I mean you cut off here, there is so much of energy that is still possible, and your E cut itself also will be so large that will tell you that that is not a good cutoff. So, 2.5 times is like second nearest neighbor, these are Leonard Jones, okay, maybe they are hard spheres interacting. But in for example EAM, there is also a cutoff, I think that goes to what Sushil, some 5 to 10 lattice parameters. 6 lattice parameters, yeah. So, and that is optimized. I mean, when they generate the potential, they will optimize and they will tell you that in this is intermetallics, for example. You can expect that second nearest neighbor is not sufficient, right, because it makes some due on 19 or something. So far it has to extend, which means the potential should have that much, and that is what Ferdi was pointing out, that okay, you can take iron and then cut off the potential somewhere, it won't even know, so it will make BCC or FCC. That is not truly what the system is doing, we are faking it. So, but here in this case it is a good cutoff.
I just call this further integration routines, yeah, to get a better approximation. It's a bit, if you do integration, you can just sum up the different intervals, but you can do this, what is it called, trapez rule or so, which gives a much better approximation. It's a bit similar to this. Then there is something called velocity valley, which is a bit similar. So what you do there is first of all, it's always the same. You start with this Taylor expansion. Plus by the way, I think Guru did not mention this. Of course, you can have different types of atoms, and you have to have different masses here for each atom. Yeah, so perhaps I should put an Mi here. At the moment, this does not matter. And then the velocity. At this time step, what do we take? We could just add the acceleration, but instead we take the acceleration at this time step and at the time step afterwards. So in a sense, it's just the arithmetic mean between time t and time, or the force at time t and time t plus delta t. So if you do the integration, you do, so for a time step from t to delta t, you compute these x of t plus delta t. Always you have to guarantee that you don't need information which you don't yet have. Yeah. So you have now this coordinates xi from I can write it here, from x of t, v of t, and f of t. So all the information from time t before, and then we compute the forces which depend on the new coordinates. Yeah? And then in the next step, you calculate the velocities here. Yeah, what else? From v of t, f of t, and f of t plus delta t. So this is feasible. Yeah, you have all the information you need, and this algorithm, I think it's even more common than the standard Valley algorithm. I think it has some better stability or so. There's a variant. I think that's this Leapfrog algorithm. I think it's called Leapfrog because it's jumping back and forth. Yeah. So there you do half time steps. So you take the t plus half delta t from this force at t. Then you can calculate the x after delta t from the x and the v. So in a sense, you interleave the calculation of the location and the calculation of the velocities. And then in the third step, you calculate the new forces. This has advantages, this algorithm, but the disadvantage is that now you calculate the position of the atoms for t plus n times delta t, and the velocity is right in between. Yeah? So if you need precise velocities for the same time as you have the positions, then you can't apply this algorithm. But I think numerically it's probably a bit more stable. And stable always means how well is energy conserved, how well is total momentum conserved, or stays zero. I think, and how efficient is it? How large can I choose the time step? That's also a very important point because each calculation of the forces is, I think, it's the most heaviest in a molecular dynamics simulation, because there you have to take all these complicated functions for the potentials. I mean, for the Lennard-Jones it's simple, but in other cases it can be quite time consuming. So you try to get the time steps as large as possible. Then there are the so-called predictor corrector. Basically, the idea is again that you first calculate new positions or new velocities with what you know, and then you do a correction step with the new knowledge. Yeah. So how do we do it? So first, do what we. Oops, sorry. That's our predictor. Perhaps I can put this with a tilde. And then now I have new positions. With these new positions, I can calculate new velocities and new forces. And what you do is you replace the velocity from the predictor step with the mean of the velocity of the new step and that of the old time. And same here for the forces. So this is a corrector step. I skipped, of course, in between you have to calculate the velocity and the force for a time t plus delta t. Yeah. But that's basically the idea, and this seems to be also quite efficient. And this predictor corrector algorithms, they can be generalized to what we call higher order methods. I think there's a year predictor corrector, fifth order or so. So this is just an expansion of this idea. Often it comes under the name higher order schemes. And I think very often you read in publications on molecular dynamics, fifth order gear predictor corrector method. Yeah, so seems to be common. So instead of stopping here this Taylor expansion after the second or after the third element, you just continue it. By the way, I was not aware that this third derivative has a name. Yeah, I think it's I don't know a German term for that. So
and there is also name for in the other way also. You say that gradient curvature.
This is skewness and this I know, but
so in mechanics, for the motion,
okay, this
jerky motion actually comes from that acceleration keeps changing.
Okay, yeah. So you continue this Taylor series. Well, these all stand for time derivatives, 1 point, 2 point, and so on. Yeah, and we give names to these terms here. Just R1. And now I can go down the line. Or R2 tilde for time plus delta t. Now is R2 plus 2R3 plus 3R4 and so on. R3 now is R3 of t. Of course, these are all at time t here, plus 3R4. If I stop at fourth order, these are my predictors. That's why I put this tilde here. And then, I don't know precisely where it comes from. There are good approximations for the corrector terms. R1 at t plus delta t. Follows from these tilde terms. with strange prefactors here. Yeah, sorry, I did not explain this delta R3. Delta R3 is a change of R3 obtained for the force at t plus delta t minus R3 for the force at t. This R3 was this third term here, so it's just this term here, which is the acceleration, so that's why the force appears here. And the R2 is obtained from these predictor values plus 3/4 of delta R3. R3 is R3 tilde plus delta 3. I mean, this is obvious. And R4 these are the corrector terms. And you can extend this scheme, and in principle, numerically, you can now make larger time steps. But I think there are other limitations for the time step. For example, that the atoms do not move too far, as I showed in the beginning. Then even a precise integration does not help you. I mean, you have the trajectories of the atoms, one side, which you want to integrate as precise as possible. But then you have the, so to say, physical limitations of your system, which give other constraints. So I think this is I think there are more of these integration routines which can be used alternatively. And once you start using these lumps, you can try whether this makes a difference and whether you get faster results or so. But typically people stay with this Verlet or velocity Verlet algorithms. I think the advantage of the other algorithms is not very big. And on the other side, you have a higher numerical effort to calculate all these intermediate quantities. You have to do a bookkeeping for much more quantities, so it's also perhaps more memory intensive. Okay, so this, I think, was this last part of these integration routines. Okay, are there any questions? I stopped the recording already, but if there are questions, we can switch it on if you want to have them recorded, or we can discuss freely without recording, whatever you prefer. But basically, it's numerics, I would say. I mean, there are clever people who discuss all the convergence properties of these different integration routines. That's one side, but on the other side, as I said, you have to keep in mind that there are also physical constraints coming from your system, not from the mathematics behind it. Okay.